Hello students, today in your calculus class we are going to work on differentiability. So let's get started. First we're going to try this quick warm-up. So this would be a good time for you to practice this on your own and then go ahead and press play. So based on what we've done in class before, we are trying to find the graph of f prime. So what I did is I made this quick table right here, and on this table I chose specific values for x as they relate to the graph. So we chose -8. So if you look at the graph, -8, -4, -1, 3, and 7. And what we're trying to do here is we're trying to find the slope of the tangent line at these specific points. So to do that, we're going to find the slope of these lines. And you'll see here that this one gives you a slope of -1. So that one gives you a slope at -1. So at -4, -8, the graph should be -1, or the slope is -1. If we look at the next line that goes from -4 to -1, that gives us a slope of 7/3. And for 3, that gives us a slope of -2. And finally, the last one gives us a slope of 0 because it's a flat line. So what happens next is we're going to try and graph these. So we know that from -8 to -4, the graph is at -1. So really, this is the point. Right here. And we know for -4, it's at -1. And because from this original graph right here, we know that that slope stayed constant, we should have a flat line like so. And when we go from -4 to -1, we saw that it changed a little bit. And because it was discontinuous, there is no slope there, but we know that from -4 to -1, it should be at 7/3, so that's about 2 1/3. So it should be from here to here. And from -1 to 3, we know that it changed to -2. So we should be down here. And finally, from 3 to 7, it was at 0. So this is what your graph of f prime should look like. So it's pretty basic because these are linear graphs, but higher order exponents are going to yield much more complicated graphs. Just a quick review. So let's take a look at differentiability. So when we're talking about differentiability, we're trying to figure out when graphs are differentiable, when we can find a derivative for it, or rather a slope of a tangent line there. So one of the things we need to talk about really quickly is the second derivative. Now the second derivative is the derivative of the first derivative. Now we denote that, as you can see here, with f double prime. With these two apostrophes, you might see it as y prime on the second line, or d2 dx squared of f of x, or d2y dx squared is another way that we look at it. Most typically, you'll see f double prime or d squared dx squared of f of x. So let's take a look at functions that are not derivative just to make it extra clear. Now, f is not differentiable where the slopes of the secant lines fail to approach a limit as x approaches a. So what that means is, if we take a look at a function from both sides, and the secant line fails to approach a limit, as in from both sides you may be getting different limits, that means it's not going to be differentiable. So here are the most important ones to consider, and these are the most obvious. So the derivative does not exist for any of the following: a corner. So let's take a look at what a corner looks like. The graph y equals x is the most prominent. Notice that at x equals 0, the slope of the tangent line here and the slope of the tangent line here are going to be going towards different things. One's going to be negative, one's going to be positive, and because they're not the same, it's not going to be differentiable at x equals 0, which again is a corner. It's a corner because it looks like a corner. The next one that we're going to look at is a cusp. So this is an extreme case of a corner where one-sided derivative approaches positive infinity and one is negative infinity. the easy example for you to look at is f of y equals x to the 2/3 power. So if you take a look here, it's curving downwards and then it's curving back upwards. So it's not quite a corner. That's why we call it a cusp. The limits there at x equals 0 are going to be different. Therefore, it's not going to give you a derivative. It's not differentiable. Next one is a vertical tangent. So vertical tangent is when both one-sided derivatives approach infinity or both one-sided derivatives approach negative infinity. So the example here is the cubed root of x minus 1 at x equals 1. So if we take a look at that graph, let me zoom out here really quick. We have the following graph, and you'll see here at x equals 1, you'll see here at x equals 1 we have this vertical tangent, which is not going to be good for us when we're trying to find that tangent because they're going towards infinity and negative infinity. So let's go back. And then of course, discontinuity. So any point that is discontinuous is not differentiable. Those are the most basic ones. So again, that is a corner, a cusp, a vertical tangent, or a point of discontinuity. Now, one of the ways we can see differentiability is if there's what's called local linearity. And local linearity means that there's a small interval that the graph looks like it's a straight line. So if we were to take a look at one of the former ones that we had, so let's take a look at this graph here. And well, let's go away from x equals 1. If we were to get closer and closer and closer to this, you could see that this line looks very much like a straight line. So differentiability equals local linearity. So it means it looks like a straight line. So let's look at another example. What we're going to try and do here is show that f prime does not exist at x equals 0, which means it's not differentiable at x equals 0. So what we're going to do is we're going to take the derivative of the equation on the left and the equation on the right. So just in the interest of time, I'm going to find the derivative for the left side already, which I know that y prime equals 2x, and I know that the derivative on the right side is y equals 1. Now if we're taking a look at this at x equals 0, I know that y prime is equal to 2 times 0, which is equal to 0. And I know that y prime here is just equal to 1. Now notice both of these limits at 0 do not approach the same thing. And because they don't approach the same thing, it's not differentiable at x equals 0. So let's examine a few more graphs. So given the graph and the domain, determine if the graph is differentiable, continuous but not differentiable, or neither continuous nor differentiable. So we're going to look at the boundary set here. So this is going to be our domain from -4 to 7. So what I'm enclosing in this box, that's our only domain. So that's the only thing we can focus on. What exists out of that is irrelevant. So first of all, we're trying to see if this is differentiable. Now because we talked about the 4 things that make things differentiable, we're going to point those out. So we could say that this is differentiable. This is part A, of course. This is differentiable at all values except when x equals 0, 2, and 6. Now the reason why we can say it's differentiable at all values except 0, 2, and 6 is actually very simple. First of all, we know that at x equals 0, there's a corner, so that's not differentiable there. We know at 2, there's a dip point of discontinuity. Therefore, it's not therefore it's not differentiable there. And then at x equals 6, there's a hole. Therefore, it's discontinuous there as well. Now, let's look at part B. Part B states which parts are continuous but not differentiable. So, for part B, it's basically it's all values except, actually let's see about the all values. It's basically all values except x equals 0, because at x equals 0 it is continuous, but it's not differentiable again because it's a corner. If we look at part C, neither continuous nor differentiable, then your answer would be x equals 2 and 6. So what I hope you may have noticed here is if you take a look at A tells you when it's differentiable, which is all values except 0, 2, and 6. And you'll notice that the types of points where it's not differentiable is composed of B and C. So B is when it's continuous but not differentiable at this corner, and then C is 2 and 6 when it's not continuous nor differentiable. So part A is made up of parts B and C, those 3 points. So that was a graphic way for us to take a look at this. Now, what I'd like for you to do is grab your TI-83 and try punching this sequence of numbers in. So if you type in math and then the number 8 or scroll down to n deriv, this is actually one way for you to find the derivative using your calculator. So the way you would input it would look like the following thing: n deriv of f of x for x and a. So notice I put this note here that it's not always correct. And the reason why it's not always correct is because it takes an approximation, which we'll talk about in just a second. So the ones that will especially not be correct is the ones that we mentioned earlier. The point where you have a corner, cusp, vertical tangent, or discontinuity. So I just want to make sure you're clear on that. So for the most part, it'll work, but not all. Now, I want you to, again, type this into your calculator. So I'll tell you how to type it in. For part A, if you type in n deriv, f of x is your function, so you'll type in 2x to the 4th, comma x, comma 2, because 2 is where we want to find the derivative of. If you type that into your calculator and you push enter, you should have gotten the following thing, which is 64 should have been your answer. If you do it for part B, e sine x, once you find the derivative of that, you should have gotten 0. For the last one, you should have gotten probably 0, but remember, keep in mind, this is not going to work because it's a corner. Now, I told you that it's not always going to work. And the reason why it doesn't always work is because the calculator is doing something called a symmetric difference quotient. And so what a symmetric difference quotient does is it calculates numerical derivatives at a very, very, very small point above and below your x value that you want to find. So if we wanted to find the value at x equals 0 for the absolute value y equals x, what it's doing is it's picking a point h that's plus the original that you wanted and a little bit below that you wanted. And so it approximates that. So it's almost the equivalent of finding f prime when the derivative exists, but on those special cases, it's not going to work. And so notice the TI uses 1/1000th of a point for it to kind of approximate that symmetric difference quotient. So again, this works fairly consistently except for the 4 points that I mentioned earlier: corner, cusp, vertical tangent, and discontinuity. So in the same way you could punch this into your calculator, you could also use the y equals to graph a derivative. So what I'd like for you to try on your calculators is going into the graph button, top left, and then nderiv, so math 8, and typing in the two functions below. And what you'll find is the derivative for each one. So if you did it for the first one, f of x equals sine x, then your graph should look like the following thing. This is what your graph should look like for y equals sine x, because the derivative of sine x is cosine x. And then derivative of y equals ln x is actually 1 divided by x. So this is what your second graph should look like. So we want to make sure we talk about it again. Differentiability implies continuity. So if something is differentiable, that means that it's continuous at that specific point. Not at every point, just at the specific point we're talking about. So one of the theorems you need to consider, and you probably want to write this down, it states if f has a derivative at x equals a, then f is continuous at x equals a. So there is a proof in your book, but you're not going to be required to memorize or show it. Lastly is the intermediate value theorem for derivatives. It says if a and b are any 2 points in an interval on which f is differentiable, then f prime takes on every value between f prime of a and f prime of b. So in English, it means that if we have a function and it's differentiable between any interval a and b, it means that every value in between a and b is also differentiable, and it exists because it's continuous. So there's going to be lots of time for us to practice and for you to ask questions. But that's all for now. I'll see you guys next time.